Welcome back, everybody, after lunch break, now to our conference on precipitation and flash flood prediction for minutes today. And we start now with our specialized session on quantitative precipitation estimation. Well, this is mainly split it into two parts. The first part before the coffee break is more on the use of polarimetric weather radars for quantitative precipitation estimation, while the second part after the coffee break is focusing on opportunistic sensing of rainfall, especially making use of commercial microwave links. And together with my colleague Christian Qualler from the Karlsruhe Institute, Campus Alpine in Garmisch-Partenkirchen, and myself, Silke Trömel from the University of Bonn, we will guide you now through this session. And as our first speaker, our keynote speaker in this session, I'm happy to introduce Alexander Ryzhkov from NOAA SSL and the University of Oklahoma. And he's talking about the most recent progress in polarimetric radar QPE.
Good afternoon or good morning, everybody, depending on where you are. And I'm Alexander Ryzhkov, and I thank Silke for introduction, and I appreciate the contribution to this talk from my colleagues Jian Zhang, Pengfei Zhang, and Yu Chen from the University of Bonn. In my talk, I will focus on two important recent developments in the polarimetric QPE. One of them is utilization of specific attenuation for rainfall estimation, and another one is a novel concept to address bright band contamination and overshooting of rain at longer distances from the radar, which we call polarimetric vertical profile reflectivity, PVPR technique or PVPR. The methodology of using specific attenuation or ROV was introduced 6 years ago. And after extensive testing and validation at S-band in the US, it matured to the point of operational implementation on the US National Weather Service network of the NEXRAD radars. And actually, the University of Bonn can be considered as the birthplace of this methodology, this technique, because the first couple of papers describing the method were written together with our German partners. And the whole idea of using attenuation was inspired and motivated by the need to quantify rainfall with X-band polarimetric radar owned by Bonn University. The microwave radiation from X-band radar is subject to strong attenuation, and that was a problem. Okay, later, this idea was tested with S-band radar in the US and proved to be particularly promising at S-band, where the relation between rain rate and specific attenuation is almost perfectly linear, although the magnitude of attenuation itself is vanishingly small at S-band. And the detailed description of the ROV algorithm at S-band and the results of its massive validation in the US are summarized in the next 3 papers, okay, shown in a list. And I expect that my colleague Jian Zhang in the next talk will provide more information about the method validation. I will just remind you its basics and focus on some challenging that still remain. Okay, how to estimate specific attenuation along the ray. We can do this from the radial profile of Z, attenuated Z, and a path integrated attenuation PIA. Okay, as prescribed by this famous formula, this well-known formula that was used in the NASA studies, for example, for decades. And it is important that in this formulation, the estimate of the radial profile of A is immune to the biases caused by radar reflectivity biases caused by radar miscalibration, partial dim blockage, and wet radon, and attenuation itself, because it's attenuated profile that is being used in this formula. Then now, how to measure PIA? It is not possible to estimate PIA with a single polarization radar, but dual polarization radar can do that. And we can simply multiply a total span of differential phase along the propagation path in rain by the factor alpha, which is the ratio of specific attenuation and specific differential phase. And once the radial profile of A is determined, then rain rate can be computed using a power law R/A relation, like that. Of course, we need some sort of the non-zero delta phi-dp, but the method works even for delta phi-dp as low as 1 to 3 degrees. It is known that specific attenuation is a function of the radar wavelength or microwave frequency and temperature. Therefore, the multiplier gamma in the power law relation and the factor alpha, which is a ratio A to KDP, depend on lambda and T as well. However, their product, okay, and the R/A estimate itself is practically insensitive to the variability of temperature and radar wavelength in a given frequency band, S, C, or X, if this exponent delta is close to 1. So therefore, a single R/A relation can be used in a wide range of temperature and radar wavelength. For example, at S-band, we are using a standard relation with the exponent very close to 1, which means that this relation is very, almost perfectly linear at S-band. The biggest problem with the method is that in addition to radar wavelength and temperature, alpha also depends on differential reflectivity, as shown at these two plots, at S-band and C-band. Okay, it depends on differential reflectivity or variability of drop size distribution. Okay, in the current version of the R/A algorithm, which we employ at S-band, the factor alpha is determined from the slope of the ZDR dependency on Z, which we call ZDR slope. And then alpha can be estimated from this slope using some sort of relation. And it's a good thing that the estimate of ZDR slope is immune to calibration errors of Z at ZDR. Okay, because all potential polarimetric radars are still struggling with the problem of the accurate calibration of differential reflectivity. The ZDR slope is determined in real time from ZDR scatter plots in rain, as demonstrated in this slide, illustrating the difference between these slopes for classical continental MCS observed in Kansas in US and Hurricane Florence also in US. So the former one is characterized by abundance of large drops, higher slopes, and smaller alpha as a result. Whereas the latter is dominated by high concentration of small drops, lower slope, and as a result, correspondingly higher alpha. The advantages and caveats of the R/A algorithm are listed in this slide. It's low sensitivity to the DSD variability because the R/A relation is very close to linear. Immunity to radar miscalibration, partial beam blockage attenuation, impact of wet rodom, everything that impacts absolute value of radar reflectivity. Then it has high spatial resolution, very similar to the one produced from R of Z, and much better than the one produced by R of KDP, because KDP has to be smooth over the radial. It demonstrates uniformly good performance for light and heavy rain, ideal for networking and compositing, particularly for the radars operating in different wavelengths. A couple of caveats. It has to be complemented by R of Z if the span of differential phase is low, and also by R of KDP if rain is mixed with hail, okay, because R of A simply doesn't work in hail. And the biggest problem actually is that the parameter alpha is variable depending on rain type and needs real-time optimization. So estimation of the alpha on the scan-by-scan basis. The immunity of attenuation-based rainfall estimates to the partial beam blockage, often caused by nearby trees and man-made targets in the close proximity to the radar, is one of the most decisive arguments that help us to sell the method to the National Weather Service community, because this difference between R of Z and R of A rain map is very convincing. I assume that Jean-Jacques will describe general validation results for R of A across US using the MRMS platform that development of which she is heading. And I would like simply to mention a recent independent validation study made by hydrologists in the Iowa flood center area, which is prone to sometimes catastrophic flash floods. And the center is led by Vidi Krajewski. And this completely independent study in the flood-prone area that is covered by 3 ATAD radars. And the radar versus gauge scatter plot summarizing observations with 2 radars over 3 years, okay, from 2015 to 2017, show obvious improvement in the estimates of daily rain totals if R of A in combination with R of KDP is used compared to R of Z. So the gray circle indicate results from R of Z and the red circles from R of A. Okay. The normalized mean absolute error is reduced by about a factor of 2, which is quite significant improvement. The problem with the current algorithm that a single value of alpha is used for the whole radar coverage area, and the spatial variability of alpha is ignored. For example, if we have the MCS in a total radar field of view with both a convective line or squall line of MCS, where dominated by large raindrops, large particles, and stratiform rain dominated by smaller particles. So we inevitably somewhat overestimate rain in a convective area, okay, and underestimate rain in the stratiform area, because we are using one sort of average value of alpha, which seems to be overestimation for heavy rain and underestimation, sometimes very significant for light rain. All right. So what to do? We were thinking about alternative ways to determine the factor alpha. And one of the possible way to take into account special heterogeneity of DSD and alpha is to compute the factor alpha for a particular azimuth, either of these two integrals. I don't have time just to explain why we use these sort of integrals, but both integrals contain this function which describes the dependence of alpha on ZDR. Okay, and if we use those, there is no need to estimate the ZDR slope. And also, since we are doing it separately at every azimuth, this azimuthal variability of alpha is captured. The problem is that ZDR could be very well calibrated. And because this, as you see, this ZDR is a denominator, and the function is very sensitive to ZDR possible miscalibration. So, and these ZDR have to be corrected for attenuation, of course. Nevertheless, the technique shows promising results, which can be illustrated by analysis of 2 cases: tropical cyclone, actually Hurricane Irene, and a continental MCS in Oklahoma. This continental case. These 2 plots show azimuthal dependencies of alpha for the 2 cases, for tropical case and for continental case, using a couple of formulas, but these two formulas give very similar results. And this already seen that it's clearly seen that alpha is generally higher for tropical rain, which is expected, 50% higher or so. Okay, that means that this technique captures this difference, in addition to capturing all these azimuthal dependencies. And as can be shown in the next slide, this azimuthal variability of alpha is anti-correlated with, or correlated, but with negative sign, with the average radar reflectivity along the ray for particular azimuth of Z and ZDR. And that means that we are actually capturing the physical essence of this sort of phenomenon, which is a good thing. Concluding the ROA topic, I need to make some comments on the effectiveness of the ROA algorithm at C-band, which is of primary interest to the European community. And Yu Chen will make a special presentation on the ROA applicability at C-band at the end of this session. And I can say that, unfortunately, there are several factors indicating that the ROA method is less efficient at C-band than at S-band. And the underlying physical reason for that is much stronger effects of resonance scattering on large raindrops at C-band than at S-band. Therefore, the ROA dependence is not as linear at C-band than at S-band. Okay. So this slide, actually, the scatter plots of R versus Z, KDP, and A are shown for C-band and S-band. Okay. At S-band and red dots indicate very tropical, or we label it very tropical, but rain that is dominated by small raindrops. And blue dots indicate the scatter plots for rain dominated by large drops, which we label as continental, very continental rain. And again, if you look at this two scatter plots, red and blue, for S-band, there is practically no difference between those. For both type of rain, it's almost a perfectly linear dependence. For C-band, yes, there is a dependence, but only for rain that is dominated by small raindrops. Okay. However, for larger raindrops that are subjected to resonance scattering effects, so we have even worse performance than for, say, R of KDP for higher rain rates. So it tells us that the ROA at C-band may work perfectly well for rain dominated by small drops, but we need to develop a criterion to distinguish between the two types of rain and use ROA for one type and probably R of KDP for another. And using a simple Z threshold is apparently not sufficient. We have to develop a little bit more sophisticated procedure for distinguishing these two types of rain. Okay. My next topic is QPE at longer distances from the radar and introduction to polarimetric VPR. The impact of the bright band and overshooting of rain at longer distances actually manifests itself as an enhancement of radar reflectivity at the distances where beam intersect the melting layer, and reduction of Z, or negative bias of Z, where the radar samples snow and ice above the melting layer. But again, the range intervals where these occurs and the magnitude of enhancement or depression depend on the height of the melting layer, its depth, height, and also its depth. Okay, it's much more pronounced errors for thick melting layer compared to thin melting layer. All right. So it also depends on the height of the melting layer, its depth, and the vertical gradient of radar reflectivity above the melting layer, especially in these regions. So in a current next-rad algorithm, this problem is addressed by using the R of Z relation with some different fudge factors. We call it fudge factors, okay, depending on the results of classification, right? Wet snow, dry snow crystals, and so on and so on. Okay. Range intervals where all these different formulas are utilized depend on results of classification. And this is sort of using these three relations with different fudge factors is equivalent simply subtracting or adding a few dBs at different ranges from the radar. It sort of partially mitigates the bias, but creates strong discontinuities in the retrieved rainfall fields. So, which undermines the credibility, our credibility in front of the users of this information. And in addition, the QPE product is vulnerable to the hydrometer misclassification. So if classification is wrong, then QPE will be wrong as well. So if you look at this, the typical PPI of Z, differential reflectivity and differential phase and cross-correlation coefficient, you see that polarimetry may offer very efficient possible solution because the areas of bright band contamination are so well delineated in terms of differential reflectivity, especially cross-correlation coefficient. Okay, so and our suggested methodology, which is called polarimetric PPR, is based on the correlation of the radial profiles of cross-correlation coefficient and radar reflectivity. Because you see that this artificial enhancement of radar reflectivity occurs at the distances almost collocated with where cross-correlation coefficients drops. Okay. So, and for this we need to first determine the height and the thickness of the melting layer, and this means that the melting layer detection algorithm and should be closely linked to the PPPR algorithm. From this slide, this slide shows that radial profiles of Z bias, differential reflectivity, and ρHV are strongly correlated. And we will capitalize on this correlation between ρHV and Z in our method. Indeed, radial profile, indeed, the deeper minimum of ρHV, here it's deeper minimum of ρHV, which curve 1, corresponds to higher bias of radar reflectivity caused by the melting layer, also profile 1 here. So the whole idea of this PPPR is simply to examine the measured radial profiles of ρHV at a given elevation and find its best match in the family of model radial profiles, which we store in the lookup table. And I'll explain it better in the next few slides. Radial profiles of delta Z and ρHV depend on the vertical profile of Z and ρHV through the melting layer, and also effects of beam broadening that has to be taken into account explicitly. And the statistical correlations between Z and ρHV in the melting layer, which were determined from the analysis of climatology of quasi-vertical profiles in the melting layer. So, and there are a couple of important papers just recently came out. One of them summarizes the results in the US, and another one with Silke Trommel as lead author summarizes the similar results for in Germany. And then the multitude of model radial profile of Z bias and ρHV at lowest antenna tilts is generated for different heights and strength of the melting layer. And these model profiles are stored in the lookup tables that can be calculated only once. Then we pick up an appropriate model profile of Z bias at every azimuth by finding the best match between the model and observed radial profile ρHV, and subtract this model profile of Z bias from the measured radial profile of Z. That's the idea. Then this is a simplified model of melting layer that we use in our modeling and generation of the lookup tables. So these are piecewise linear profiles of rho HV and Z are assumed, and every radial profile of C cross-correlation coefficient is labeled by two parameters, so indexes like height of the bottom of the melting layer and the strength of the melting layer, which sort of depends on the depth of the melting layer, but not only on that, and I will explain that in the next slide. And in our current version of the algorithm, 120 radial profiles of rho HV and delta Z are generated for a given antenna elevation, corresponding to 15 values of the bottom of the melting layer, and 8 values of the depth of the melting layer. And the depth of the melting layer is very strongly correlated with minimal value of rho HV with the melting layer. And again, these are intrinsic true profiles of rho HV and Z in the melting layer. So we need to take into account the effect of beam broadening at longer distances and project those sort of profiles onto the radials. Okay, it's once we projected those profiles to the radials, so we're getting some sort of model profile of rho HV like that, and the measured profile of rho HV at the same elevation can look like this. And it turns out that there is no need to store full 120 radial profile of cross-correlation coefficient. So because each profile can be characterized by two important parameters that can be robustly estimated from the observation. One of them is just the onset of the impact of the melting layer along the radial. So where there's a distance to the cross-correlation dip. Okay, and also the strength. What we meant by the strength of the melting layer is the area between this some level, threshold level of cross-correlation coefficient and its curve. Okay, and these things can be estimated quite robustly and reliably from the measurements. Okay, so instead of storing 120 radial profiles, we store parameters R of B and S in the two lookup tables or matrices 15 by 8 for each antenna elevation. And again, I reiterate that such lookup tables have to be generated only once. And this is an example of the lookup table for parameter RB, of distance to the melting layer, okay, as a function of the height of the bottom of the melting layer and true depth of the melting layer. Okay, so you see this this distance RB, the function of both parameters, okay, HB and depth of the melting layer. The similar things for lookup table for S. Okay, so it's again, it depends on both parameters. So how the algorithm works? So we are measuring two parameters, RB from the measurements, from the observation, and S, and using these two tables, okay, we're estimating what is the closest bottom of the melting layer and what is the closest true depth of the melting layer, okay? Or we can simplify now the indexes of the HB and indexes of the S, that is characterizes the depth of the melting layer. You know, in the meanwhile, we are doing something very useful for melting layer detection, and we already have the product, MLDA product, or the map of the height of the bottom of the melting layer in the case, for example, of sloping melting layer, which is clearly seen from the PPI image of cross-correlation coefficient. So you see, we are able to generate this new product for NextRad, which is a map of the melting layer bottom height, and we can generate also the map of the melting layer bottom top height, melting layer top height. Okay, so this is a case of the sloping melting layer where there is no snow but just rain. And there is a case when we see the sharp transition from pure snow to wet snow or rain. And again, the MLDA product shows very well where we have snow and where we have melting layer with the height as a function of both azimuth and elevation, sorry, distances from the radar. Okay, but anyway, it's only one small step from MLDA to PVPR QPE. So then once we determine those indexes characterizing the height of the melting layer and strength of the melting layer, we simply pick up the appropriate radial profile of delta Z, the Z bias, from the model, from the number of the model profiles. Okay, and a corrected radial profile of Z is obtained simply by subtracting this delta Z from the corresponding to the model profile from the measured profile. Okay, from measured radial dependencies of radar reflectivity. And then I will, in the remaining time, I will, because I don't have much time left, but anyway, I'll show a few examples of how it works. This is a fields of radar reflectivity cross-correlation coefficient at half a degree elevation. Okay, S-band radar, next rad. And this is corresponding radar reflectivity cross-correlation 1.45 degree elevation. Okay, so you see clearly, especially at the high elevation, the impact of the bright band contamination here. All right. Then what happens when we do this PVPR correction? This is radar reflectivity at elevation half a degree before, 145 degree before and after. Okay, you see first that, especially if you look at high elevation here, that those artificial enhancement or radar reflectivity are totally gone. And moreover, we are adding more reflectivity, and we are addressing also underestimation of radar reflectivity at longer distances from the radar that caused by overshooting. Another important thing is that look how similar the profile after PVPR correction look at lower elevation and a high elevation. This means that if lower elevation and data at low elevation somehow compromised, either by partial beam blockage or the impact of the ground clutter or whatever, we can always switch to the higher elevation without fear that that bright band will hurt our results. Okay, that's especially important for in the areas with complicated, complex terrain. That's another example also from the next rad, and again, clear artificial enhancement of radar reflectivity associated with bright band contamination. And this is what happens after we correct this radar reflectivity using PVPR. And again, there is no artificial discontinuities or something like that. Everything is very smooth and nice looking. Also, with the help of my colleague, Yu Chen, I got this DWD data from a C-band radar, one of the C-band radar, and you again see the same things, the same sort of contamination at PPI of 1.5 degrees and 0.5 degrees in the DWD C-band data. Again, 0 HV, ZDR, and so on. Okay, and this is the result of correction. So before PVPR correction, this is what we observe in terms of radar reflectivity in PPI at 1.5 degrees, at this 0.5 degree. And after PVPR correction, again, you see tremendous improvement. And also we see, I mean, a lot of consistency between lower elevation and high elevation. This means that we can use high elevation, which may look more clean, because here you see some sort of impact of the ground clutter contamination at low elevation, which is gone if you use high elevations, right? So that's very important practical implication. And again, what Yu Chen actually sent me a few days ago, She also, for a couple of radars for one particular event in Germany, actually shows that how much better, I mean, the ROZ with the PVPR correction works compared to the situation when no PVPR correction is made. All right, and just again, I'm finishing, and there are a couple of things which I would like to simply mention in passing. So, so far, in all our previous analysis, we assumed that the rain rate below melting layer doesn't depend on the altitude. This is not the case if significant evaporation occurs in the dry layer below the melting layer. And the difference between rain rate just below the melting layer, okay, and at the surface, depends, first of all, on vertical profile of humidity, and also on size distribution of the raindrops, say, below the melting layer. So for rain dominated by smaller raindrops is much stronger affected by evaporation than rain with the same intensity, but larger raindrops. And the Martinitis scheme, just that MRMS people using to take into account evaporation, takes into account, I mean, vertical profile of humidity, but not drop size distribution. So, and again, this is a plot from our old paper with Matt Comjan, showing that for a given vertical profile rate of humidity, rain rate will lower differential reflectivity. This differential reflectivity on the x-axis evaporates faster. So in other words, we need to take into account both. I mean, ZDR and also relative humidity vertical profile. And this is a very low-hanging fruit, and I strongly recommend to the real PEP community to probably consider this as a task for the phase 2 of real PEP. Opposite situation when humidity is very high below the melting layer. Warm rain production is more likely, which is manifested by much higher rain rate near the surface and aloft. Okay, so than aloft. So this is manifested by very strong vertical gradients of rad reflectivity, differential reflectivity, and also specific differential phase. Okay. Taking a warm rain process that is dominated by coalescence and breakup into account is much more difficult than taking account evaporation process in the case of dry layer. And this will be the next frontier of our research. And I don't believe that it's a very, very common situation in Germany or in Europe in general, but it's mainly for Asia and mainly for south of the United States, or tropical cyclone situation. But that's a very important problem that needs to be addressed. And finally, I'm getting to conclusions and wrap up my talk. Yes, the success was demonstrated at S-band for ROA, and the decision has been made for operational implementation of this algorithm in US NextRAT network. Several issues remain, and we find looking for solving those issues. And one thing that you have to keep in mind that the ROA technique seems to be less efficient at C-band, but not useless. All right, because the use of ROA relation has to be complemented probably by more aggressive utilization of RF-KDP relation. That's a message. Regarding conclusions for PVPR, we believe that this technique passed the feasibility test. It's equally applicable for S and C band. Okay, should be no detrimental impact of C band on that. I expect. So, and again, it's important that it makes a good use of high antenna elevation in a situation with data at lowest elevation of poor quality due to ground cloud contamination or beam blockage. And that's the end of my talk. Thank you for your attention. I'm ready for questions.
Thanks, Alexander.
Oh, sorry, I was muted. I was already talking, but you cannot.
So you
I was
take over,
talking
Silke.
and talking. Oh, sorry.
Thanks, Alexander.
I just said we had already some questions via Slido, and I think one of the first questions popped up from Marco Gabella from Meteo Swiss. I'm not sure whether he's logged in one of our rooms. Does somebody know? Otherwise, I will just forward his question. So he was wondering what is the reason or the origin of this azimuthal dependence of alpha you were talking about.
Oh, the reason is simple, because you've seen that the factor alpha depends on drop size distributions and depends on a differential reflectivity. So you can, in one azimuth, you may have a rain characterizing, which is characterized by very high ZDR containing many large drops. In another azimuth, you simply don't have those type of rain. You have more stratiform rain with smaller raindrops. And that ensures the approach that we are advocating now ensures, when we take into account azimuthal dependence, that these facts are taken into consideration.
Okay, thank you, Alexander. I think that in case Marco Cabella is not happy with the answer, he can reply again, but I think he should. Seems like that. And there was also a question by Clemens Zimmer, who is also in the speaker room, so he can talk directly. Clemens? At least I see him. Clemens? Clemens, are you muted? Clemens?
Yeah. Can you hear me?
Now, yes.
Yeah.
At least I see him.
Okay, can you hear
Clemens?
me now? Huh?
Clemens, are you muted?
No,
Clemens?
I'm not. Yeah. Can you hear me?
Now, yes. At least I see him.
Okay, can you hear
Clemens?
me now?
Oh my God, there are some echoes.
Clemens, are you muted? No, I'm not. Can you hear me?
You have to unmute the stream, Clemens. I have to mute the stream.
Oh my God, there are some...
So, does it work now?
Now
Yes.
it's better.
Okay.
Clemens, do you
So
want to
does
go
it work
ahead with
now?
your question? Now it's better.
I don't know what the problem is. Okay. My question was, Alexander,
Clemens,
first,
do you want to go ahead with your question?
thank you.
Now it's better.
I don't know what the problem is. No. Okay. Silke, better read the question. Thank you.
So for some reason there is a problem when Clemens wants to say something. So he decided I better read the question for him. So he was asking, given the complication of determining alpha, what are the main causes of the azimuthal variability of the crucial alpha part? Huh? Oh no, I skipped into the wrong line. Oh no, sorry. I was now confused while I was reading, and sorry. So Clemens was asking, given the complication of determining alpha at C-band and the assumption that the information is in the polarimetric data, should we not try artificial intelligence to learn?
You know, I always, probably because of my natural conservatism and maybe age, I do believe that we always have to exhaust all these ideas resting on a solid physics before trying artificial intelligence. I know that this is a very, very, a big buzzword nowadays and so on. Absolutely, you know, just I simply may not have a clear idea of how to use artificial intelligence in this particular case, and I do believe we still need to think about some physical problems, physical essence of the phenomenon, and see how we can address that. That's all I can say, Clemens.
Okay, thank you, Alexander. And maybe I have a quick associated question. So you said, if I understood correctly, you are considering the azimuthal dependency of alpha, but doing no segmentation along the radial, right?
Yes, I believe that, yeah, you need segmentation along the radial once you have, say, rain mixed with hail. This does require segmentation. And again, the way you do that segmentation, it is a little bit tricky thing, and you have to do it very carefully. But because of this complex nature of such segmentation, I believe that we can use it only in a situation when we have hail mixed with rain along the propagation path.
Yeah. And given you are using this azimuthal, or taking into account this azimuthal dependency, I was wondering that you impressed that your according rainfall feed looks very, very smooth. You never see some azimuthal lines or so caused by this variation of alpha from one step to the other. Are you using some additional smoothing, or is in your case also the alpha not changing so much that it's not visible by eye? Or
you know, I can tell you, we didn't do much of this validation, this technique. Pengfei Zhang is now involved in that type of work. But again, it is always, I mean, whenever you're dealing with atmospheric phenomenon, is always to do some aggressive median filtering along azimuth especially. So, but so far we haven't seen those.
Okay, thank you. Are there more questions, urgent questions via Slido or from somebody in the rooms? If not, I would say thanks again to Alexander, and we should move on to the next speaker.